Alright, this is my attack chain presentation for my pentesting class graduate assignment. To begin this presentation, I'll be walking you through the exploitation for a designated target machine located at the IP address 172.26.75.192. This is called the park. During the initial phase of this engagement, I performed an active discovery scan using Nmap, specifically utilizing the SV flag for service version detection and the SC flag to run default enumeration scripts. This initial scan immediately revealed a high-density attack surface, most notably featuring an instance of Apache Tomcat on port 80 and Jenkins on CI/CD dashboard running on port 8080. I specifically selected this machine as my primary target because of the presence of that Jenkins instance. In a real-world corporate environment, CI/CD or continuous integration and continuous deployment servers are considered crown jewel targets for any attacker. Because these servers are responsible for building, testing, and deploying software, they are often configured with high-level system permissions and sit at a critical intersection of the network. They frequently contain sensitive source code, API keys, and automated credentials that can lead to total organizational breach. My objective for this engagement was clear: to achieve full system compromise, transitioning from an unauthenticated external viewer to obtaining root level privileges. By doing so, I intended to demonstrate the catastrophic risks posed by exposed management consoles and show how a single point of failure in an application layer service can lead to a complete takeover of the underlying Linux infrastructure. So, moving into the reconnaissance phase, my primary objective was to map out the attack surface of the target at 172.26.75.192, or the park. For this, I utilized Nmap, the industry standard network mapper. As you can see on the screen, the specific command I executed was nmap-sv-sc 172.26.75.192. To break down those flags, I used -sv for service version detection, which queries open ports to determine exactly what software and version it's running. This is critical because vulnerabilities are version specific. I also use -sc, which runs a suite of default scripts from the Nmap scripting engine. These scripts check for common misconfigurations and can often pull back extra information like HTTP titles or SSH host keys, saving me a lot of manual work later on. The results gave me a very interesting spread of services. First, I noticed two distinct web servers: Apache Tomcat 9.0.108 on the standard HTTP port 80, and Jetty 12.0.22 powering a Jenkins instance on port 8080. Seeing two web servers on one machine is a red flag. It often suggests a development environment or a complex CI/CD pipeline where different services are being bridged together. I also took note of port 2049, which is running NFS, Network File System. In a penetration test, NFS is always worth a look because if it's misconfigured with no root squash or has public read access, an attacker can sometimes mount the file system remotely to steal sensitive data or even inject SSH keys. This was the case, but I'm not focusing on this. This is how you got access to Benson. While I did a quick check here for open shares, my attention was quickly pulled towards the more complex application layer. The ultimate pivot point for this engagement was clearly port 8080. Jenkins is a feature-rich automated automation server. Because of its complexity, it is frequently the weakest link in a lab environment. The Nmap output confirmed it was an active Jenkins dashboard. Complex services like this often have management interfaces that, if not properly locked down, provide a direct path to the underlying operating system. This realization dictated my next move, shifting from a broad scanning to targeted application level enumeration of Jenkins. 3. Vulnerability identification. Once I identified Jenkins running on port 8080, I navigated to the web interface to see how it was configured. To my surprise, and from attacker's perspective, my delight, the instance was completely unauthenticated. I was greeted immediately with the Jenkins dashboard. In the world of security, an exposed administrative dashboard is like finding a master key left in a door lock. The specific weakness I moved to was to investigate Jenkins' groovy script console, as you can see on here. Now, it's important to understand this isn't a bug in the traditional sense. It's a legitimate built-in feature designed for administrators. It allows them to run groovy scripts directly on the Jenkins controller to perform maintenance, automate tasks, or troubleshoot the environment. However, because Groovy is a powerful language with direct access to the underlying Java runtime environment, this console is effectively a remote code execution (RCE) vulnerability by design, if it isn't protected by a login. If you can reach this console, you aren't just managing Jenkins, you are directly talking to the operating system. To validate this vulnerability, I didn't jump straight into a complex exploit. In a professional pen test, you always want to start with a low and slow validation to confirm execution without crashing the service or triggering unnecessary alarms. I navigated to the /script endpoint and ran a very simple one-line command: print lm whoami.execute.text. I'll never forget that aha moment when I clicked run and the console immediately printed back the word Jenkins. That was the definitive proof of concept. It confirmed that the server was not only receiving my input, but was actively executing my commands on the system shell and returning it as output to my browser. At this point, I had moved beyond a mere web visitor. I had confirmed that I had the power to execute any command I wanted on the target machine as the service user. This validation turned into potential finding in a critical vulnerability setting, setting the stage for the actual exploitation phase. 4. Exploitation. Now that I had validated the remote code execution, it was time to move from a web-based console to a fully interactive command line interface. To do this, I utilized a reverse shell script written in Groovy. Before we look at the code, it's important to understand why we use a reverse shell instead of a bind shell. In a standard setup, a firewall would likely block any attempt made to connect directly to a random high-numbered port on the server. However, most firewalls are much more permissive with outbound traffic. In a reverse shell, the target machine, in this case Jenkins, initiates the connection back to the attacker machine. By having the victim call home, we effectively bypass the most ingress firewall rules, making this a staple technique in modern pen testing. Let's look at the Groovy script I injected into the console. The core of this attack relies on two main components: the socket and the process builder. First, the script defines a socket pointing to my attacker IP, 172.16.16.110, on port 4444. This establishes the communication tunnel. Next, it initializes a process builder with the command /bin/bash. This is the engine of the exploit. It tells the operating system to start a bash shell. The script then meticulously redirects the input and output streams. Essentially, it takes whatever I type on my machine, sends it through the socket, and feeds it into the bash process on the server. It then takes the server's response while I pipes it back into my screen. The while loop you see at the end ensures the connection stays alive and responsive until I decide to close it. While the script was ready on the Jenkins side, I first had to prepare my own machine to catch the incoming connection. For this, I used netcat, often called the Swiss Army knife of networking. I ran the command netcat-lvnp4444. Let's break down those flags. L tells netcat to listen for a connection rather than initiate one. V is for verbose output, so I can see exactly when the connection is established. N tells it to not resolve host names, which speeds things up and prevents DNS leaks. And -P4444 specifies the exact port I told the Groovy script to call. With the listener active, I clicked run on the Jenkins console. Within a second, my terminal transformed. As you can see in the screenshot, the netcat listener reported the successful connection from the target IP. I immediately typed "Who am I?" and confirming that I was now operating a live interactive terminal as the Jenkins user. This marked the successful exploitation of the application layer and gave me a foothold I needed to begin exploring the internal system. Post exploitation. Now that I had a foothold in as the Jenkins user, the real challenge began, moving from a restricted service account to full system control. This phase is broken down into two parts: lateral movement and privilege escalation. My first goal was to see what I could access. In a Linux environment, the etc shadow file contains the hash passwords for every single user on the system. Normally, a low-privileged user like Jenkins shouldn't even be able to look at this file. It's restricted to root for a reason. However, during my enumeration, I discovered that the Jenkins process was either heavily misconfigured or running with the cap DAC read search capability. This essentially gave the process the power to bypass file read permission checks. I simply ran cat etc shadow, and to my surprise, the file scrolled right across my screen. I immediately copied the hash for the user Rigby and moved it over to my attacker machine for cracking. To crack the hash, I used hashcat. I want to take a moment to explain the methodology here. I chose a dictionary attack over a brute force attack. A brute force attack tries every possible combination of characters, which can take years. A dictionary attack, however, compares the hash against a list of millions of common passwords. in this case the famous rocku.txt word list. I used hashcat mode 1800, which corresponds to SHA-512 Unix hashes. You can identify these by the $6 at the beginning of the hash string. I used because the password was incredibly weak, password is password, hashcat cracked it in less than a second. This was a massive win for the attack, but a total security fail for the user Rigby. With those credentials, I was able to SSH back into the machine as Rigby, giving me a much more stable and professional shell environment. Once I was in as Rigby, I needed to find a path to root. I uploaded a tool called linpeas, the Lineage Privilege Escalation Awesome script, to automate the search for vulnerabilities. linpeas highlighted a critical finding. The system was vulnerable to CVE 2021-3560. This is a fascinating vulnerability in Polkit, which is a service that handles sudo-like permissions on the modern Linux desktops and servers. The technical reason why this works is due to a race condition in how the dbus-send requests authentication. If an attacker sends a command to create a new admin user but kills the process at a very specific millisecond, specifically while Polkit is still asking who is asking for this, the system essentially gets confused. Because the UID of the requester disappears before the check finishes, Polkit's logic defaults to authorized rather than denied. To exploit this, I used a Python script from GitHub that automates the precise timing. I used wget to download the exploit directly onto the target machine. After setting the execution permissions, I ran the script as Rigby. Within seconds, the script exploited the race condition, bypassed Polkit's security checks, and created a new user with the root permissions called Unicord. I logged in as Unicord with the password Unicord. I then ran sudo su to change to root, and I officially bypassed all security layers of the operating system. 6. Objective completion improved. As you can see here, I am wgetting the script from my own Python server, and I named it exploit1.py. It then downloads exploit1.py to Rigby's home directory. You then run exploit1.py with Python 3 exploit1.py. It then runs Unicord, which is, I'm assuming, the name for this, and or the name for the user. And I've then switched users to user Unicord, and then I sudo su, and then I am now root. As you can see at the very bottom, root at the Park desktop. 7. Lessons learned and mitigations. It's Evil Jenkins, and it's PwnKit. As we conclude this walkthrough, it's vital to discuss the defensive takeaways. This attack chain was a perfect storm of misconfigurations, but each link in that chain could have been broken with standard security best practices. First, for the Jenkins administrator, the primary lesson is the absolute necessity of authentication and access control. The entry point for this entire compromise was a management console left open to the public. In production environment, management interfaces like Jenkins, Kubernetes, or Docker should never be exposed to an open internet without multi-factor authentication, and ideally they should be accessible via a VPN or trusted internal network. If the Groovy console hadn't been locked down, the attack would have stopped at the front door. Next, we look at the user Rigby and the importance of password hygiene. While the breach started at the application layer, I was only able to pivot deeper into the system because Rigby used a password that was easily crackable. A complex, unique passphrase would have significantly slowed me down, potentially giving a security operations center time to detect the unauthorized Jenkins activity and kill my initial shell before I even moved to a user account. For the system administrator, the lesson is patch management. The jump from a standard user to root was made possible by CVE 2021-3560. This is a well-documented patched vulnerability. Maintaining a rigorous patching schedule for core system utilities like Polkit is one of the most effective ways to prevent local privilege escalation. An updated system would have stopped this exploit entirely, leaving me stuck as a low-privileged user. Finally, we must address the principle of least privileged. During my post-exploitation, I discovered the Jenkins service had the ability to read the etc shadow file. This is a massive violation of least privilege. Service accounts should only have the bare minimum permissions required to perform a specific job. By giving a web-facing service unnecessary read access to sensitive system files, the administrators inadvertently provided me with the roadmap to compromise for the rest of the users. By addressing these four areas, access control, password complexity, regular patching, and strict permission scoping, this entire attack path could have been mitigated at every single stage. This has been my attack chain presentation. Thank you so much for watching, and have a wonderful day.